Equations are often treated like static lines of text, but they actually describe physical shapes. We can take these abstract rules and translate them into landscapes we can navigate. By the end of this lesson, you will calculate, plot, and hand draw a perfectly accurate graph of the equation y equals x squared. To follow along, you only need two things, a pencil and a blank piece of graph paper. Plotting these numbers is how we see the relationship between x and y. It takes a calculation and makes it visible. Right now, your paper is an empty grid. We must establish a navigation system before we start plotting. Draw a horizontal x-axis across the center and a vertical y-axis. Their crossing point is the origin at 0, 0. These axes divide the map into 4 quadrants, numbered 1 through 4 in a counterclockwise circle. Each location on this grid now has a fixed address. By drawing axes, you've created a map where every numerical pair exists at one specific point. To find our points on this map, we follow a specific rule, the function y equals x squared. Set up an x and y table, writing -3 to +3 for x. Calculate y by squaring each x. -3 squared is +9. Completing the math gives 7 distinct coordinate pairs. These pairs act as our coordinates. Without this data, we have no way to mark our positions on the grid. To plot these, always move horizontally along the x-axis first, then vertically along the y-axis. These movements have mathematical names. The x move is the abscissa, and the y move is the ordinate. To plot -3, 9, start at the origin, move left 3 for the abscissa, up 9 for the ordinate, and mark it. Repeating this for the other pairs reveals a U-shape resting on the origin. Connect the dots with one smooth, continuous curve. This curve is called a locus. It represents every possible point that satisfies our equation, turning the math into a visible shape. Now that the shape is drawn, we can use the derivative equation to measure exactly how steep the curve is at any point. A robot at x equals -2 has a derivative of -4, a steep downhill slope. At the origin, the derivative is 0, making the path completely flat. Moving to x equals +2, the derivative is +4, climbing steeply uphill. The graph shows the shape of the path, but the derivative gives us the dynamic data, the exact steepness at every moment along that path. Look at your paper. You have taken a numerical rule and turned it into a visual representation of change. You've mastered the entire sequence. You started with an equation, calculated the values, plotted the points, drew the curve, and used the derivative to find the slope. To practice this, flip your paper over and try making a new table and graph for the equation y equals x cubed. Now that you've connected the math to the motion, you can use these same steps to visualize how other equations change and grow.